reactors are the same. When you hear the phrase nuclear reactor, what comes to mind first? Most likely, a nuclear power plant, a reactor, splitting atoms, generating heat and electricity. Sounds straightforward, but in reality, not all nuclear reactors are built to produce electricity. There is a special class, research reactors, and their purpose is completely different. Key differences. Power reactors are the workhorses. They run 24/7, feeding megawatts into the grid to power cities and industries. Research reactors don't feed a single watt into the grid. Their purpose is to generate a powerful stream of neutrons. There are no turbines, no generators, no steam cycles. The key product here is the neutron flux, which enables scientists to test materials for fusion reactors, space, and advanced fission systems, produce medical isotopes for cancer diagnostics and treatment, develop and test new nuclear fuels, modify semiconductors through neutron transmutation of silicon, carry out fundamental experiments in solid-state and nuclear physics. A research reactor is not a miniature power plant. It's a versatile scientific tool. But are these reactors safe? It's a fair question, especially in the shadow of major nuclear accidents like Chernobyl and Fukushima, which have led to public skepticism, even toward research reactors, despite their much lower risks. In fact, many of these facilities are now being shut down, and new ones are rarely built. But is this justified? Let's take a closer look. What makes a nuclear reactor safe? Not backup diesel generators, not complex automated control systems, not triple redundant cooling pumps, but simple, reliable physics. Today, we'll explore one of the safest and most reliable cooling systems ever used in a research reactor. A system that requires no electricity, no pumps, and no fans. It operates purely on gravity, boiling, and airflow. How is this reactor designed? The reactor core is located in an open pool of water, several meters deep. Its thermal power is moderate, ranging from tens of kilowatts to a few megawatts. Under these conditions, it's possible to implement a two-loop passive cooling system. The first loop uses natural circulation of water around the core. The second loop uses natural air convection to remove the heat. First loop, natural water circulation. The principle is simple. Water heats up in the reactor core, becomes lighter. It cools down in a heat exchanger, becomes heavier. This density difference between the hot and cold sections drives the flow. And all of this happens without any pump. But we can make this effect even stronger by using boiling at reduced pressure. Boiling at reduced pressure. If you lower the pressure, water boils not at 100 degrees Celsius, but at, say, 70 degrees Celsius. This creates two major effects. One, a drastic drop in the density of the upward flow due to steam formation. Two, a significant increase in buoyancy, which greatly enhances natural circulation. To implement this in practice, a vacuum line is connected to the circuit. The circulation pipes are raised 9 to 10 meters above the pool. A heat exchanger is installed at the highest point. How it works? Water in the core heats up to about 70 degrees Celsius. At a height of 7 meters, where pressure is around 30 kilopascals, it starts to boil. Steam forms, density drops, the flow accelerates upward. In the heat exchanger, the water cools and condenses. In the return line, it no longer boils and is denser. A significant density difference appears between the rising and falling sections. which creates a self-sustaining loop of coolant flow. Self-regulating system. This system is fully self-regulating. The more thermal power the reactor produces, the higher the water temperature. The higher the temperature, the earlier boiling starts. The earlier the boiling, the stronger the circulation. In other words, when the reactor gets hotter, the cooling intensifies automatically. No electronics, no control systems. Second loop, air cooling. So where does all that heat go? Into the second loop, cooled by ambient air. Air passes through the heat exchanger and warms up. It rises naturally through a tall chimney. Cool air is drawn in from below. The cycle repeats. All of this is driven by natural convection. Hot air is lighter than cold air. Summary: 2 passive loops. So the entire cooling system works like this. Water circulates on its own, thanks to boiling and density differences. Air circulates on its own, thanks to natural buoyancy and heat. No pumps, no fans, no valves, no motors. Reliability. This is practically an ideal cooling scheme, completely independent of the power grid. No moving parts that can break. Operates solely on fundamental physical principles: gravity, boiling, convection. And gravity, as we know, doesn't require maintenance and never fails. Simplicity equals low cost. This system is not only reliable, but also inexpensive. A low construction costs, no complex machinery, minimal maintenance, easily scalable to different reactor powers. Time to change the perception. It's time to rethink how we see research reactors. Despite their engineering simplicity, systems like these can ensure stable and safe operation over a wide range of reactor powers. But here's the paradox. The development and deployment of such passive systems is rarely funded. Yet they hold the key to cheap, reliable, and inherently safe nuclear facilities. Think about it. The cooling system we just described is simpler than the radiator system in a regular car engine. And yet the phrase nuclear reactor still sounds to many like something dangerous and incomprehensible. It's time to change that. Final thought. A safe nuclear reactor is not science fiction. It's engineering reality.